The $10,955 Tesla Model 2 has ignited a wave of curiosity across the automotive world. Is this new entry-level price point truly about making electric vehicles obtainable for the average buyer, or is it more of an experimental test? A bold step to gauge how far affordability can go without sacrificing Tesla's signature feel. The name Elon Musk alone carries shock value, and with each new project, people wonder, is the surprise in the price tag, the design materials, or the way manufacturing itself changes the game? When Tesla hints at a prototype, the question always follows, is the innovation in what you can physically touch, like the doors, seats, or roof for in the unseen numbers, the hidden efficiencies that quietly save owners money every single month? In the Model 2, that question finds its answer through a series of clever engineering choices designed to push cost, comfort, and performance forward simultaneously. A roof that redefines lightweight design at the top of the car. Tesla introduces what it calls a light roof concept, a crucial example of minimalist engineering at its finest. Instead of the traditional panoramic glass found in many of its higher-end models, the Model 2 uses a prism-structured polycarbonate sheet. This choice achieves two objectives: reducing weight and cutting cost. Polycarbonate, a tough and transparent engineering plastic, has a density of about 1.2 grams per cubic centimeter, nearly half that of tempered glass, which sits between 2.4 and 2.6 grams per cubic centimeter. That single change may seem minor, but when applied to something as large and elevated as a car's roof, the results are significant. Swapping out a full glass panel for a heat-formed polycarbonate sheet reduces the roof's mass by roughly 12 to 18 kilograms. It's a small percentage, around 0.8 to 1.4% of the car's total weight. Given that the Model 2 is expected to weigh between 1,300 and 1,500 kilograms, but weight saved high above the center of gravity has an outsized impact. Less mass up top means improved stability, reduced body pitch during acceleration or braking, and less energy wasted correcting those tiny rocking motions. Over time, this adds measurable efficiency. City driving range can improve by 1 to 2% simply because the vehicle requires less torque correction and smoother power modulation. But Tesla didn't stop at weight savings. The polycarbonate roof plays another crucial role: temperature control. It's coated with ultraviolet blocking and infrared filtering layers. These coatings can reject about 99% of UV radiation and roughly 80 to 85% of infrared light. The effect is immediate and practical. When parked under harsh sunlight, the Model 2's cabin stays between 4 and 6 degrees Celsius cooler than a car with an untreated glass roof. That might not sound revolutionary, but when you climb in and turn on the air conditioner, the system doesn't need to work nearly as hard to bring temperatures down. In that first hour of use, electrical savings can reach 5 to 7%. For a small battery vehicle like the Model 2, every percentage counts. Those micro savings translate into lower total ownership costs and longer life between charge, especially for daily users who park outdoors. Manufacturing efficiency was also a driving factor. Polycarbonate is softer and easier to form than glass, which means the heat-forming process can take less than 90 seconds on a dedicated thermoplastic line. Lower temperature requirements cut energy use in production as well. And if a roof does get damaged, replacement is far more affordable. A new polycarbonate light roof panel, including labor, costs around $180, compared with $800 to $1,200 for a traditional panoramic glass roof depending on location. This massive difference directly impacts lifetime maintenance costs. For budget-conscious buyers, the ability to replace large body parts easily and cheaply adds peace of mind. Hail damage, falling debris, or a simple scratch doesn't translate to financial pain. Beyond practicality, Tesla added a subtle touch of beauty. The prism finish on the polycarbonate surface is designed with microscopic structures that refract and diffuse light. The result is a soft, glowing interior atmosphere that minimizes glare while still allowing sunlight to fill the cabin. It feels premium even though the cost is low. With an abrasion-resistant top coating and excellent transparency, passengers still enjoy a panoramic experience minus the heat buildup and weight penalty. All of these improvements reduced mass, lower heat load, faster manufacturing, and affordable repairability combined to deliver something rare in an entry-level EV: efficiency without compromise. Tesla managed to make the Model 2 lighter, cooler, cheaper to maintain, and yet still elegant. It's a perfect example of the company's strategy to engineer beauty through logic, comfort on long drives. The motorless air cell set long drives are often the true test of how refined a car feels. In this area, the Model 2 introduces another smart yet understated innovation: the motorless air cell seat. The goal was simple: deliver the comfort of high-end massage seats without the bulk, complexity, or cost of traditional motorized systems, instead of using heavy electric motors and gear mechanisms. Tesla's seat design integrates a set of thin, air-filled bladders beneath the back and thigh cushions. These bladders connect to a small 200-gram microblower and a compact air accumulator chamber. Controlled by solenoid valves, the system creates a gentle sequence of pressure waves that simulate kneading and pulsing sensations. The feel is surprisingly luxurious, yet the setup consumes minimal energy. Each seat draws only about 8 watts, while traditional multi-motor massage seats can require 40 to 60 watts. On a 3-hour road trip, that equates to just 0.1 to 0.2 kilowatts of energy usage. Given that the Model 2 consumes roughly 12 to 15 kilowatts per 100 kilometers in the city, this reduction effectively adds hundreds of meters or even over a kilometer of extra driving range over time. Weight savings are equally impressive. By removing the heavy motor assemblies, Tesla shaved off 2 to 3 kilograms per seat. Across both front seats, that's 4 to 6 kilograms less weight, or about 0.3 to 0.5% of the car's mass. Again, a small number in absolute terms, but one that meaningfully reduces roll inertia during lane changes and tight maneuvers. Every kilogram counts in an efficiency-first car. The ergonomic benefits are what drivers will feel most. The system alternates air pressure between 20 and 40 millimeters of mercury across different contact points. This pattern gently shifts body weight and encourages microcirculation, reducing the numbness and stiffness often caused by static seating. Tesla's internal tests suggest back fatigue can drop by 15 to 20%. Compared to standard fixed foam seats during drives longer than 2 hours, there's also subtle ventilation. Air flowing through the seat fabric helps keep passengers' backs dry and comfortable in hot or humid weather. Despite this airflow, the system remains whisper quiet. Measured noise levels stay under 30 decibels at head height quiet, enough to disappear into the Model 2's already well-insulated cabin. Durability and simplicity are other unsung victories. Traditional motorized massage seats rely on several mechanical parts: motors, shafts, and gears that wear out over time. The Model 2's air cell seat reduces moving components by about 70%. The only active elements are the blower and a few valves. Automotive-grade microblowers are rated for more than 20,000 hours of operation, and maintenance typically involves nothing more than cleaning a dust mesh filter, if replacement is ever needed. It's inexpensive, around $35 per seat. In contrast, repairing or replacing a conventional massage module can cost between $200 and $300 plus labor. This approach perfectly matches Tesla's philosophy for the Model 2. Offer a premium tactile experience that's sustainable, durable, and low cost over years of ownership. In short, Tesla has taken the sensation of luxury seating and distilled it into something simple, energy efficient, and affordable: proof that comfort doesn't have to come with high weight or maintenance costs. Sealing out noise with smart materials. Another area where Tesla's engineers rethought convention is cabin sealing. The subtle but vital interface between the door and body frame. In luxury vehicles, a soft, quiet door close is part of the premium experience. Traditionally, this effect is achieved using a motorized latch system. You lightly push the door, and a small motor automatically pulls it shut for the final few millimeters, ensuring perfect alignment and an elegant thunk. However, these electromechanical systems are complex and costly. Each door requires a motor, sensors, gears, wiring, and control software, adding $300 to $400 in parts alone, plus several kilograms of extra weight and more maintenance points. Tesla's challenge with the Model 2 was to replicate that high-end feel without the expensive machinery. The answer? Smart materials instead of motors. The Model 2 uses a combination of dual-stage air gaskets and alignment magnets. When you push the door closed, the air gasket compresses smoothly during the last 5 to 10 millimeters of travel. This compression dampens the impact and creates a soft, progressive closing feel. Simultaneously, the small embedded magnets guide the door edge into precise alignment with the frame. Applying a gentle pull that completes the seal, the result is a balanced force curve. Closing the door requires only 30 to 35 newtons of effort. Compared to 70 newtons for many conventional cars, the experience feels refined yet effortless. Acoustically, the improvement is quantifiable. The most sensitive range for human hearing lies between 1 and 2 kHz. The exact frequencies prod.